we were talking about graphs, right? So now we can talk about directed graphs. Why is this not working? Die. Undie. Would that work? Yeah. The size of the screen changed. So. Depending on what you're doing, graphs may be undirected. Basically, your relationship is bidirectional. What did we call it in math? Well, basically, it's Facebook, right? If you are my friend, then I'm your friend, right? They are. My brain is not working. There is. It's not bilateral, you would remember.
Symmetric?
That's not symmetric, right? When you have a relationship and no, A and B are related implies that B and A are related.
Yeah. Oh, transitive.
Transitive, not transitive. Transitive A, B, and B, C.
Reflective?
Reflective, right? Reflective. Yeah! Thank you. Thank you. Right? Reflexive. No? Not reflexive?
Itself, yeah. Reflexive is when it's itself.
Reflexive one
Yeah,
itself.
it has to be
You mean
symmetric.
symmetric
Yeah,
property.
it's symmetric.
Symmetric?
Yeah.
No.
Yeah.
You're kidding me.
Google's your best friend.
Oh, what if we had the fountain of all knowledge? Of course, I'm gonna go to Bing
Symmetric.
just to bug people. Metrical relationship, maybe? Marriage, no. Math. Yes. Yes. Wow. Okay. I'll believe you. Yeah. Basically, they talk about symmetric relations, right? That's what an undirected graph does. Many times we have directed graphs where the arrows actually have a direction, right? If you think about Facebook, they don't, right? Which other thing that looks like Facebook does have directed relationships? Yes, right? If I follow you on Twitter, you don't have to follow me, right? So those become directed. What other examples of graphs would be more directed than
Love triangles.
love triangles? Yeah, love relationships, right? I love my wife. She may or may not love me. Hope she does. Oops, this is being recorded. Never mind. Let me stop the recording. Travel, right? We were talking about airports and travel, right? And so there's a direct flight from here to Houston, but there may not be a flight back from Houston to here, right? Doesn't happen with those airports, but it may happen with small airports, right? For flow and traffic, right? Stuff may not be symmetrical, so it may be better to represent it like this, right? Even like the internet is connected both ways, but depending on your provider, you may get a lot more download than upload speeds, right? So it would be better to represent it as two different links, right? So we still have the same thing. It's a graph is a set of vertices and a set of edges, but now the edges are directed, and we say that an edge UV leaves node U and enters node V. The order starts becoming important, right? That's the only difference, right? Another example is a web graph, hyperlinks, right? I link, one page links to another, the other one doesn't have to link back, right? And so if a bunch of people link to one page, then that probably means that that other page is important. And so Google will put it higher on this search, right? In that example, your nodes are web pages, your edges are hyperlinks from one page to another, and one of the things of the PageRank algorithm is looking at that kind of stuff, right? And you can see, isn't this cool? You can see the, oh, it's interesting. The timing is interesting. Look at the links. CNN, okay, that makes sense. Netscape.com, does anybody go to Netscape anymore, right? I mean, you go to Mozilla, Novell, I guess they still exist, but I haven't heard from them in ages. CNN is high, I'm assuming some CNN. TimeWarner.com, okay. HBO and Game of Thrones, okay. It's like, that sounds a lot newer than Novell, I don't know. How long has Game of Thrones been going on? 7th season? 2010? Did anybody cared about Novell in 2010? I don't know. In roads, right? Thank goodness most places in Atlanta we don't have that problem, except in downtown, right? Streets are one way. So it's actually important, right? And you may need to go around big chunks before you can go where you wanted to go, right? So on a more realistic thing about streets, then you have to think about the direction of the streets, right? And the intersections are the nodes, the edges are one-way streets. This was which blog links to each other, and again it was the direction was important, right? Ecological food webs, who eats who, right? That's important. A lion would eat a gazelle, not the other way around. Some tons of examples, right? Has anybody heard about WordNet? When you have a chance, it is really cool. It's kind of a it's a computer dictionary-ish, but it's not just a dictionary, it has synonyms and things like that. So it's a very cool natural language processing kind of dictionary, which if you like computers, is probably interesting from computers. If you talk, it's probably interesting from a language perspective. On scheduling, right, you may have precedence constraints. Financial, the transactions are actually directed, right? One person paid the other. Some other things, right, may or may not, like cell phone, right? Who started the call may be important. Sometimes it may not be, right? Infectious diseases, who can infect you? Games, again, board positions. Moves takes you to other board positions, and you may not be able to undo the move, right? You cannot unroll the dice in Monopoly. Citations, journal articles. When you think about programming, right? An object has a pointer to another object, and the other guy may not have a reference back. Inheritance, control flow, who jumps where, right? Basically, again, everything can be a graph, right? And most of the things you could say, oh, if I really need to, I could do it as an undirected graph, but it's not terrible to represent it as a directed graph, right? Do I lose anything by making a graph directed? what happens if I have an undirected graph, but I want to see it as a directed graph? What can I do?
Remove some links. I mean,
Or the other way around, right? Make the links, right? Add another link, right? When I have a link, now I add one going from left to right and one going from right to left. And that's it. Now it's directed. Right? What would be the problem? Well, now I have twice as many edges, so my algorithms may take longer, right? So if I know that it's undirected, then life is good. But if not, it's not that big of a deal. A lot of my algorithms become similar, right? Directed reachability, give it a node S, find all nodes reachable from S. Directed ST, shortest path. Graph search, breadth first search extends naturally to directed graphs, right? I can just only I follow the edge if there is a directed edge. And it's the exact same thing, right? At the time it was important. Web crawlers work exactly this way. We normally don't really do web crawlers anymore. I guess people still do sometimes. Normally Google and Bing and Yahoo and those guys do web crawlers and nobody else does. But sometimes you do, right? You need to scrape web pages and then follow links and stuff. Some more definitions. Strong connectivity. Nodes U and B are mutually reachable if there is both a path from U to B and also a path from B to U. That is also what? A cycle, right? A graph is strongly connected if every pair of nodes is mutually reachable. Let S be any node, right? G is strongly connected even if every node is reachable from S and S is reachable from every node. You don't really need to test everybody with everybody, right? Having it with one node would ensure it works both ways, right? If it is strongly connected, then of course, for any node that you choose, right, every node connects to that one and that one connects to every node, right? Because that's the definition of strongly connected. But if you only know that everybody can connect to this node S and this node S connects to everybody else, right? What do you do if you need to go from A to B? Well, I'll go from A to S and then from S to B, and so I can go from A to B, right? And so every node would be connected with every other node. Now, how can I determine if G is strongly connected in order of n plus n time, right? Pick any node, run breadth first search from S in G, and then run it, but now in reverse, right? And that will tell me whether I can reach every node from S and whether from every node I can reach S. And if that is true, then it's strongly connected. If not, it is not strongly connected. So in this case, the second graph is not strongly connected. Where can I not go to? From this guy to this guy, right? I can go from top left to bottom left, but not from bottom left to top left, right? Is that what you were saying?
Oh yeah, it's the only one you can't leave and then somehow get back.
Oh, yeah. Well, yeah, but that also means that this guy is also not connected to a bunch of people. Actually, neither one of the bottom ones are connected to a bunch of people, right? Oh, and actually nobody comes into this one either. So, yeah. There is tons of stuff, right? A strong component is a maximal subset of mutually reachable nodes. What does maximal mean? If you add one more node, it doesn't work anymore. Does that make sense? So in this case, 0, 2, 3, 4, 5 is a strong component, but 0, 2 by itself, right, the set of the nodes 0 and 2 is not, because I could add 3 and it's still strongly connected. Right? So in this case, how many strongly connected components do we have? And they were nice and they grayed them out. How many do we have? Can you count?
12.
Okay, good. We have 5, right? And there. Sorry. And there is a theory that tells you that you can do that, right? There is another cool thing we can do with graphs. When you have a directed acyclic graph, am I pronouncing it correctly? Close enough. Sounds good enough for you. Is a directed graph that contains no directed circuits. And that is cool because it allows me to sort of kind of sort things, right? A topological order of a directed graph is that it's an ordering of the nodes so that for every edge vi, vj, we have I less than j, right? So we can just rename these things, right? Renumber these guys from 1 to 10 so that all my edges go from left to right. If the graph is not acyclic, can I do this? No, because the cycle, right? The one that cycles back would need to go in the other direction. Does that any make sense? So this is a partial ordering. This is important. This gives you kind of a greater than relationship or something like that. Right? It's actually not complete because you cannot necessarily. In this case, actually, yeah. In this case, you can't really. There is no good reason for doing V1 and V2, right? They just makes it pretty, right? But you could sort it the other way around, right? Put V1 and V2. That would still be a topological order. For example, if you have precedence constraints, right? H, Bi, Bj means that Bi must occur before Bj. For example, course prerequisite graph. And for you guys, they are not that deep, right? Most of our graduate courses don't have deep chains of prerequisites. But when you were an undergrad, you tended to have that stuff, right? You need to take this one before that one, and all of that stuff. When you're thinking about something like Make, or Gradle, or Maven, or all of the other 100 Make things, one module or one file needs to be compiled before another because it calls it, right? Computing jobs, all sorts of things, you end up with these kinds of things. It's very similar to this kind of directed acyclic graphs, right? what's the problem if you have cycle here? I'm doomed, right? I mean, you need to take computer 1 before computer 2. You need to take programming 1 before data structures and data structures before programming 1. You're doomed, right? That's not going to work. So, now there is an interesting lemma theorem, which is if G has a topological order, then G is a directed acyclic graph. And so basically what we are saying is this idea of if we have a topological order, we cannot have a cycle because this guy would be out of order. Does every directed acyclic graph have a topological order? And how can we do it, right? We can. Doesn't necessarily have a unique one, right? But if G is a DAG, then it has a node with no entering edges. Because if not, we would have a cycle. If it is a DAG, then it has a topological ordering, right? Because, well, if n equals 1, actually, if n equals 0, I have no nodes whatsoever, so it works. So, given a directed acyclic graph on n nodes, right? Find a node with no entering edges, and that shows that the one with one less, if I take that node, cannot create cycles. By induction, we have a topological order, and so just add that node with no edges to it, and that will work. And that gives us a algorithm for computing a topological ordering, right? Find a node with no edges, put it first, right? Take it away from the graph, and recursively do that with the now smaller graph where you took an edge out. Sorry, a node out, right? Does that make sense? Do we always find the same DAG? No, right? There could be that at some point in time, or at many points in time, you have two nodes with no incoming edges, right? So you could choose either one as the first one. There is an algorithm for finding a topological sort in order of m plus n. For every node, we are going to have is count the number of incoming edges, right? S is the set of remaining nodes with no incoming edges. I initialize that count and that S, and then I find somebody without, with that count being 0, remove, decrement the count for all of them, right? And if the count becomes 0, then I add it to the set of remaining nodes with no incoming edges. right? And for every edge, this is order of 1, so we are good. Right? Close enough. Any other questions? This is all you need to know about graphs. Isn't that cool? Now we're going to go learn more stuff about graphs. Administrivia. I am going to stop assigning assignments because I cannot grade them. I'm actually gonna make maybe one assignment for chapters 3 and 4, right? Just remember that you still need to know this stuff, right? I'm just not gonna grade it. Does that make sense? So don't just say, oh, they never, right? He never asked me to do any exercises, so I'm never gonna do them. And I will try to grade assignments 1 and 2 over the weekend. Maybe. I tend to not do this. I tend to grade fairly quickly because I still have to grade anyway, right? So there is some point in delaying, but I'm not grading enough. Assign and do sample grading?
No, you just make an assignment and
No grading?
just be like, hey, this would be a good thing to look at.
Okay, I will do that. Shall we do? What would work better for your work habits? And don't worry, those are my work habits too. Shall we do? We can do two things. One is they are assigned and not graded at all. The other one is they are assigned and I do sample grading. Basically, I'm going to grade 10. You don't know which 10, right? And so,
That one's scary.
sorry?
That one's scary.
Yeah.
Yeah, scary, but it's scary.
Why is it scary? I mean, you
There's
just,
an unknown element.
why? Why is it scary? You just have to do all of them anyway, and you have to get 100 on all of them anyway. That's what you do. You're graduate students, right? I mean,
It's just fear of the unknown.
okay. Then I'll make them ungraded.
I do like the fact that having assignments, just because I assume that your assignments are somewhat similar to what you'd have on the tests.
Yes-ish.
Yeah.
Yes.
Yes. This is the first time that I've done this class, so as of right now, I have no clue how I'm going to ask this stuff on the test, right? I will know the night before the test.
There's that fear of the unknown.
I tend to make my tests from previous iterations of the class freely available, but I've never taught this class. I have no clue whatsoever.
So you're gonna make a test on GitHub and
I
as collaborators, and we can all make it together,
yes,
or at least. a
and then I
practice test.
divide the grade by 23.
You can do that for a practice test.
I will try to make a practice test. I'll try to do that. I tend to do that, and that also gives me a good idea of what's good to ask. Now we start with the cool stuff. Actually, graphs are really cool because they are applicable to everything, right? And so the more you learn about graphs, the more they are kind of, in a way, math is magic, right? And the more magical tools that you have at your disposal, the more problems you are able to solve, right? If you can say, rather than, oh, I have no clue how to approach this problem, you can say, oh, that's just minimal flow, right? That's just minimal distance among nodes, right? And so even if you never go and solve it, you know that it's a solved problem and you can go to sleep, right? So graphs are a great tool for that. We are going to start having even more fun by looking at tools for designing algorithms, right? When I see a problem that I have never seen, what do I do? What do you do when you see a problem that you have never seen, you have to solve? Google it. Okay, sorry?
Understand it. What they
Try to understand it, right?
Compare it to a similar problem.
Yes, if you can map it to a similar problem, right, then life is good, right? And it's like, oh, then I'll just modify it a little bit, right? That tends to be kind of one of our standard strategies, which is, in a way, Google it, right? That just gives me tons of similar problems. Playing with it to understand it, right, until I can find what's similar, that's good, right? We will see 3 or 4 meta strategies for coming up with algorithms, and both for understanding algorithms and for coming up with new ones. This is mainly giving you more things to find similar to, right? Because problem solving is hard to teach. Some would say impossible, right? Because it's like, well, if it's a known problem, then yes, but you just memorize it. But if it's not a known problem, right, then I cannot really teach you how to solve it. But by giving you more strategies and more things, right, I give you more chances of finding ways to solve it, right? One of the coolest things are greedy algorithms. Coin changing is one example. Greed is good. Now, what's a greedy algorithm? What's a greedy person? How would you define somebody who's greedy? What do they do?
Take as much as they can as fast.
Take as much as they can right now. What was your definition?
don't want to spend.
Don't want to spend? That's not being greedy. That's being the other thing, right? Like frugal or a miser, yeah. Right? Being greedy is, ooh, if I see 10 candies, I take all 10 of them, right? Take all the money I can, or all the whatevers I can, right? In algorithms, what does it mean? Well, given choices, right, I take the one that looks the best right now. And then I don't give a hoot about the future, right? I'll just do whatever seems cool right now. And then after that, I do whatever seems cool, right? Do whatever seems coolest for the hour that's coming, and then whatever seems coolest for the next hour. Is that a good strategy in life? No, right? That's why you're here. Chances are that you didn't decide that the best thing you could do on a Wednesday afternoon was come to algorithms class, right? But you're doing this because, right, it will satisfy some master plan or something like that, right? But in many algorithms, many problems, we can actually do that, right? An example is coin changing, right? And this is something that you do all the time, right? You have a bunch of coin denominations, right? In the US, we have 1, 5, 10, 25, and 100 for dollars, right? These are like, so we have a penny, a nickel, a dime, and a quarter, right? So how do you give change? You have to do 89 cents in change, right? What you would try to do is as many quarters as you can, and then as many dimes, and then as many nickels, right? That's greedy. I just, rather than check all the possible combinations, right? I'll give you as many quarters, right? And then I'll give you as many dimes, and then I'll give you as many nickels, right? So at each iteration, add a coin of the largest value that does not go past, right? That is the cashier's algorithm. It's what people normally do, right? You probably don't even think about it after kindergarten and first grade, but that's right. That's kind of how you give change. Is it optimal? So how a property of an optimal solution, right, would have pennies being less than 4, Because if you had 5 pennies, right, then optimal, what's optimal? The number of coins, right? So the least number of coins. So if I have 5 pennies in my solution, then I can just replace those 5 pennies with 1 nickel, right? The number of nickels would have to be less than or equal to 1, because if I have 2, I can just change those 2 for dime, right? In fact, when we are on the receiving end, we tend to do that, right? They're giving us stuff, and it's like, oh wait, I happen to have a dime here, so I'm gonna do this, and you give me another quarter because I don't want to carry coins, right? You don't do that? I seldom do because I usually just don't carry coins anymore, or cash of any way. It's cool, unless I go back home. In Mexico, people don't take credit card for everything. But so the number of quarters is going to be less than 3, right? Because if I have 4, then I can give you $1. And the number of nickels plus dimes would have to be less than or equal to 2. Because if I have, right, I have 2 nickels, then I could change it for dime, right? And if I have 2 dimes and a nickel, then I can change that for a quarter. So for US coins, right, the cashier's algorithm, which is a perfect example of a greedy one, is optimal, right? And we could prove this by induction. Is the cashier's algorithm optimal for any set of denominations? No, it is not, right? Depending on what you have, right? And I guess at some point in time, those were denominations of stamps at some point in time. I have no clue what we do now anymore. I haven't actually mailed anything in ages. Email is free. Ish. Somebody's paying for it. So depending on what you are doing, right, you may not. If the denominations, right, don't satisfy certain properties, then that would not work. For example, with those denominations, if you were trying to do 140 cents, the cashier's algorithm would do 100 plus 34 plus 6 penny ones, whereas I could do 270 cents, and that would give me 140. Right? Actually, the cashier's algorithm may actually break, right? If I had denominations of 7, 8, and 9, the cashier's algorithm, I'm trying to do 15 cents, I would do 9, and then I have 6, and I don't have anything 6 or less. So I just sit and cry, right? Whereas the optimal would be 15 cents, which is 7 and 8. Sitting and crying is actually an action, as any kid who's trying to do this would demonstrate in kindergarten, right? So, what is a cool thing about greedy algorithms like this one? When they work, right? What's the cool thing about this algorithm?
It's always optimal.
Well, it's optimal, right? That's cool because it works, right?
Efficient.
It's
Simple to
efficient,
write.
it's simple to write, right? It's simple to explain, and it's actually, we're gonna see that it's usually very efficient, right? I just do the easiest possible thing, right? For some definition of easiest, the thing that seems the best right now, right? What's gonna be the problem with greedy algorithms? They don't always work, right? And so before you start doing this, you need to go and say, hey, let me see if I can verify that this will work, right? And that it will be optimal. In many cases, greedy algorithms tend to give me stuff that sort of kind of works. But we're still, we end at 15, not at 45, right? I will ask this in every class. I have the class right after this where we end at 45, so I can never remember which one. So greedy algorithms are cool when they work. Interval scheduling is another example, right? Bless you. If we have jobs for a machine or some resource, right? Two jobs are, and a job starts at Sj, a job J starts at Sj and finishes at Fj, right? And two jobs are compatible if they don't overlap. The goal is to find a maximum subset of mutually compatible jobs. What can I do? What can I do that is greedy? There's actually different definitions of greediness. What seems like a possibility? Why would you start at A? Oh, is it biggest or is it at the beginning? So it's the biggest. You start at A and who would be next? G, right? So what you're saying is start with the biggest, right? And then eliminate all the guys who are not compatible, right? That's one way. What other ways could we be greedy?
Probably the smallest. Because
Well, we could
yeah.
smallest, right? What else could we do?
The one that starts the first.
Yes, just do the first one you can, right? So we're going to see that not all greediness is equally good, right? So we could, right? The greedy template would tell you just sort the jobs in some natural order, right? Choose the best one, right? The one that looks the best, and then eliminate the one that are not compatible, right? So we would have several possibilities: earliest start time, earliest finish time, shortest interval. So actually the smallest ones, right? Fewest conflicts. Earliest start time wouldn't really work, right? That would be a counterexample. If we use the shortest interval, that wouldn't work. Fewer conflicts, that wouldn't work. Actually, the one that's going to work rather than the biggest, right, is going to be the earliest finish time. Not the earliest start, but the earliest finish, right? And there is theorem. Let's see, right? Is it optimal, right? So, well, mathematicians tend to like proof by contradiction, and if you can think of a proof by contradiction, those should be easy to understand, right? Let's assume that greedy is not optimal, right? So let's I1, I2, I3, right, up to Ik denote the set of jobs selected by greedy, and J1, J2 to Jm denote the set of jobs in an optimal solution, right? And we'll call R the first one for which R is the bunch of indices for which those two solutions are the same, right? Because we don't terribly care about, right? They both chose the first three the same, so that's okay. Now let's look at the the rest, right? In here, right, you would need some job, right, that is ending at a later time. It's still compatible, right? But it ends at a later time than the solution that we're trying to do. Well, can this be any better than this? Can choosing this one leave me in a better state than choosing this one? Right?
You can.
How?
Less confidence.
Sorry?
Less conflict.
Well, I cannot have less conflicts, right? Because I have, right? Let's see. I can only do one, right? So I could, if I choose one, right? I could just replace this one with this one. And that would be better, right? Sorry, and in this case, right, maximal means number of jobs, right? So that's important. Maximal means number of jobs, not occupation of the thing. And so choosing the job that ends first and the other one would leave me in a better position. Right? I have less stuff that is conflicting. Does that make sense? So for number of things, right, that would be optimal. So if I have to find the minimum number of classrooms to schedule all lectures, right, I could use this algorithm. For example, right, this is basically the same algorithm, right? Consider the lectures in some natural order, assign each lecture to an available classroom, and then allocate a new classroom if none are available, right? That's kind of our template. We could do earliest start, earliest finish time, shortest interval, or fewest conflicts, right? Again, in this case, actually, earliest start time would get us the best thing. It is, right? Yeah. How can I implement this fast in an order of n log n time? I could store the classrooms in a priority queue, right? And I can just find for every lecture J, right? Check. Sort them by start time, right? And then check the next available classroom. And that's order of log n. Am I telling you dumb things? I probably are. But you believe me. Isn't that cool? Now, let's stop here because I don't know what I'm saying anymore. And we'll continue next class. I wasn't planning to reach here.
Too efficient.
Too efficient.